Hello, and we are back. This time we are understanding compensation in acid-base cases from the perspective of the blood gas data. You'll recall that the blood gas data is where we get all our best information, and it deals with metabolic with bicarb, and it deals with respiratory with PCO2. So this is lungs, this is the rest of the body. The pH here is 7.25, which is low. So there's some sort of acidosis going on in the system. Then we have to figure out which system is driving that problem. Is it PCO2? Well, PCO2 is actually low. So no, it's not PCO2. This is an acidosis. And we look here, and bicarb is about 5 points below the reference interval. So this is, the pH is being driven by bicarb. So this is a metabolic acidosis. Then we have to figure out what's going on with PCO2. Is this compensation, or is this a problem all by itself? Looking at the equation, we're getting rid of CO2 from this solution, and that is trying to draw hydrogen ion out of circulation and trying to fix the pH. Bicarb is decreased, that's why I've made it small. And this is just the reference interval for PCO2 shown here beside the solution. So we're trying to make this solution more basic by losing respiratory acid. But is this compensation or a primary problem? We need to look at Dr. Valverde's equation, which is that we expect a 0.7 unit decrease in PCO2 for every unit decrease in bicarb. So we want to lose PCO2 by 0.7 for every point below the bottom of the reference interval we are for bicarb. So we're at 5. So the equation becomes 0.7 times 5 equals 3.5. Evidence of adequate compensation, and again, we won't be doing math on my final, but you may have to do this for Valverde at some point, certainly in 4th year. If this were adequate compensation, then the value for PCO2 would have been 30.5. It's currently 10 points below that, 20.5. And how did we figure this out? How did we get it 30.5? Well, since we're taking CO2 out of the system, we take that 3.5 off of the bottom end of the reference interval. And we'll talk about differences in that in a moment. Okay, so getting back to this case, we are at 20.5. This has taken too much respiratory acid out of this situation. You can never compensate too much, and this looks like too much compensation. And if it looks like too much compensation, then it's a primary abnormality. So in this case, this was an animal who had a pre-existing metabolic acidosis, and then it had to go to surgery, and we put it on a ventilator, and it got ventilated excessively. So too much gas exchange, too much oxygen going in, not a problem, except for oxygen radical generation. But too much PCO2 coming out is generating a problem in and of itself, which you'll have learned about with Dr. Valverde. So this is too much, and it is a respiratory alkalosis. So in the end, what we have is a mixed situation. We have mixed metabolic acidosis coupled with this artificially induced respiratory alkalosis. All right, and for Valverde, if you had to figure out whether it was adequate, inadequate, or its own primary problem, we figured out in that case it's already a primary problem. If we did the calculation and the result ended up being anything less than 3.5, then that would be evidence of inadequate compensation. So it would have been anything between 31, say, and 35.5 or 31 and 34, as I've written here. So that would have been evidence of inadequate compensation. I can't make you do that on the final or on any exam because I don't make you do math, but Valverde might, I don't know. All right, next case. Let's start always by looking at pH. So you figure whether it's an acidemia or an acidosis or an alkalosis. It's decreased, so this is an acidosis of some kind. What is driving that process? Well, I've got bicarb here, but bicarb is higher than the reference interval. Therefore, we've got more bicarb coming into the system. That's obviously not driving an acidosis. PCO2 must therefore be the problem. And certainly we see it's 20 points above the upper end of this reference interval. So what has happened here? We've got too much CO2 in the system, which is driving the equation in the forward reaction and generating more acid, which is titrating out the bicarb, supposedly. But we've got more bicarb. So we have to figure out, do we have compensation? My suspicion is that we do, but let's do the math and figure that. Like I say, we need to add bicarb to the system to fix it in order to figure out whether we have been trying to fix it adequately or inadequately. We do the calculation, and that is a 1.5 unit increase in bicarb is what is expected for every 10 unit increase in CO2. Well, I just said we're 20 units above the reference interval. Divide that by 10 and we end up with 2. So we are 2 times too high. So we multiply 1.5 by 2 and we end up with 3. Perfect or adequate compensation in this individual would be if bicarb were at 33. Bicarb happens to be at 33, so this is considered adequate compensation. So it's compensated just a little bit. It hasn't compensated wildly. It hasn't fixed this acidosis. It's never going to fix the problem. It's going to try, it's going to fall short, but we need to know whether it's adequate or inadequate. This happens to be adequate compensation. It's just done a mild increase. Now looking at this next case, what's going on? We have a pH of 7.36. No problem, it's right within the reference interval, but there must be a problem because bicarb is very high. So that's a very high bicarb, 10 points above the reference interval. PCO2 is also very high. Again, that is 20 points above the reference interval. This one is 10 points. So we have a respiratory acidosis because we've added a bunch of CO2 to the system. And we have a metabolic alkalosis because we've added a bunch of bicarb to the system. What on earth is going on? pH is normal because they've pulled so far in opposite directions that the pH is in the middle, more or less. So whenever you see a normal pH on a blood gas, but you've got wild derangements in these things, that means there's a mixed process going on. So this mixed process happens to be going in opposite directions, alkalosis, acidosis, and then we end up with pH that's still in the reference interval. So that is one way of doing that. And there's obviously no compensation going on, nothing to calculate in this case. The answer would be mixed metabolic and respiratory blood gas problem. So I hope that's helpful, and I'm going to try and get some more things put up today about acid base. Okay, take care.